Hey everyone, Mr. Fritz here, and in this video we're going to talk about the law of cosines. We've been talking about non-right triangles and finding different side lengths and angles of non-right triangles. So we need a little bit more than just regular SOHCAHTOA trig. And what we're going to talk about with the law of cosines is trying to figure out scenarios where you have perhaps a side length and an angle and another side, but you want to find what this third side is. We can't really do that with the law of sines, which we know right now. We need to have one of these opposing sides. So if we had one of these opposing side angles, then we could figure out what this side is, but right now we don't have a way of doing that if we're just given this information. So that's one type of a triangle we'll talk about. We'll also talk about if you have a triangle where you know all three sides, how would you find out what the angles are? You're going to need the law of cosines to figure that out, since we can't do it with the law of sines. So let's dive right into it. Some things that you'll need to know how to know how to understand before moving forward is understanding what the side, and side angle, side triangle congruence means, and that those make unique triangles. You need to know how to use the law of sines. You need to know your Pythagorean theorem. You got to know some general right triangle trig, because we will talk about right triangles a little bit to try and get us towards the law of cosines for non-right triangles. So we're going to start off with this triangle here. And I want you to think about, can you find what all of the angles are? Really, I'm going to actually take away all of the angles and say, I'm really concerned with this angle A. Can we figure out what this angle A is? Right now I have three sides, and I don't have any other angles. So could I use the law of sines? Well, no. I would need, if I were given any one of these angles, then I could use the law of sines and set up those ratios. But since I don't, I'm going to have to be kind of clever here. So I want you to see if you can't find what this angle A is. So we're going to need a new method to get there, but I'm going to kind of give you a hint to see if you can't figure this out. And my hint to you is that you should draw in two right triangles. So imagine this is like a right triangle over here, and imagine that this is a right triangle here. So you're going to need two right triangles to try and figure out what this angle is. You're also going to have to use Pythagorean theorem with each of these two triangles. Let me also throw out there that it would probably be helpful to call this height h. You're also going to need to somewhere in the mix use cosine with these right triangles that you've constructed. And really the last thing that I'd say is to break up that 13, this base here. And really, like, we've arbitrarily, or not arbitrarily, but we've dropped this altitude, and that's going to separate this 13, this base of 13, into two segments. And we can really call this, this segment we can call just x. And if this is x, then this must be 13 minus x. So with this type of idea, kind of pulling out these right triangles and using these tools, you should be able to kind of come up with what this angle is. It's a little bit lengthy, but I challenge you to take a few minutes and see if you can't figure it out before moving on. And when you're ready to go, you can resume the video and we'll go through it together. Okay, so here is my, my altitude that I've dropped with my right angle, and let's see what I'm going to do here. Do I have one more slide? No, okay. What I'm going to do is I'm going to, like I said before, I'm going to get rid of this, and I'm going to call this x, and I'm going to call this 13 minus x. So let's come up with some equations that we can determine based off of these two right triangles. If I take a look at my right triangle on the left, let's call that the blue right triangle. Here's some things that I can write about this triangle. Using the Pythagorean theorem, I can say that x squared plus, and if I call this h, h squared equals 12 squared. I also know that if I'm interested in finding this angle, I could write some trig ratios that use this 12 and use this angle. I could say that the cosine of angle A is going to equal the adjacent over the hypotenuse, so that's x over 12. I could say that the sine of A is equal to h over 12. I could write something about the tangent being h over x, but now those are both unknowns, and I got a feeling I'm not going to be using that. So let's just kind of leave this for what we know so far. And then let's take a look at this other right triangle. Let's use this green here and kind of separate this right triangle and do the same thing over there. So I can write the equation, this time would be 13 minus x, that's one leg, squared plus h squared equals 11 squared. And I'd have to multiply these two together, so that's really 13 minus x times 13 minus x plus h squared equals 11 squared. Once I multiply these two together, I get 169 minus 26x plus x squared plus h squared equals 121. And I'm not really interested in any of these angles, so I'm not even going to worry about drawing these trig ratios up. But now at this point, I have two equations that have x, and actually let me do that in another color. I've got two equations that have an x and an h. I've got this one, and I've got this one. Wouldn't it be nice if I can combine these and eliminate one of these variables? And that's what I'm going to do. I'm going to basically solve this equation for h and substitute it into this one, so I don't have to worry about any h's anymore. So let's rewrite this equation in terms of h. So h squared should equal, that'll be 144 if I square that 12, minus x squared. And then I'm going to take that whole quantity and I'm going to substitute it in for this h. So why don't I continue down here in green here. So that's going to be 169 minus 26x plus x squared. Now I've substituted this 144 minus x squared in, so that'll be plus 144 minus x squared, and that's all equal to 121. All right, so I just combined those two triangles, those two Pythagorean theorem triangles into one equation. And what's nice about that is two things. Number one, no more h's. That's good. We've eliminated an entire variable. And number two, maybe you've spotted this already, but I have an x squared and a negative x squared. So if you thought we were talking about a quadratic, rest assured, no quadratic here. Those x squareds, they cancel. So let's kind of simplify what we have in this equation. And I have 169 plus 144. You know what I'm gonna do? I'm gonna move the 169 and the 144 over here on both sides. So I'll subtract the 169 and I'll subtract the 144 on both sides. And that comes out with a negative 26x equals, and that should come out to be negative 191 once you punch that into your calculator. And let's scroll down a little bit here. So that means I could solve this thing for x, and I would get x equals 7.346. Okay, great. Now what? So I found x. That is this. All that work was really just to find this one piece right here. This x is this x. So I kind of figured out how I broke up these triangles. How does that get me to what this angle A is? That's kind of, does that help us? Well, it does, because remember, I had said before, the cosine of A is equal to x over 12. If I know what x is, I know what 12 is, I can find what angle A is. Whew, okay, we're doing it. So let's take this, and I'm going to rewrite this cosine of A is equal to this x, 7.346 over 12. And if I take the inverse cosine, that'll be A is equal to the arc cosine or inverse cosine of that whole mess, 7.346 over 12. Punch that into my calculator, and A is equal to 52.3 degrees. Woof. That is quite a bit. I know this angle, and really we could find angle B, we could find angle C. Now we can use the law of sines, because we've got one angle and all these opposing sides, and that should be enough. I'm going to stop there because I think we've exhausted that. All of this was quite a bit of work just to find this one angle. So is there a better way? Yes. Let's come up with a generalization for any triangle, not just this one in particular, but for any triangle with sides A, B, and C. So let's talk about these two triangles. Really, there's two types of triangles that are not right triangles: acute triangles and obtuse triangles. And the goal here is not to memorize this process or even be able to repeat it, but I just want you to kind of see it. I want you to write down really only the constructions and any equations you see. So I just want you to kind of have it so you can see it and refer to it. But at the end, we're going to come out with a formula. That's the kicker. That's the thing that I want you to take away from this. So what I've done here is I kind of jumped ahead. I have these two triangles, and I want to generalize that whole process that we did in the last slide. So the thing I did first is I kind of dropped these perpendiculars, these altitudes, and I kind of split up my base, or in this case added to my base. So what I like to do is kind of jot down some of the equations, pause it if it's confusing, and I really want you to make sense of how I got through each step so that you know where this formula comes from. So what I've done here is I've dropped the perpendicular from C to AB. In this one I've extended my base, and I've got my h for my height and my x for these segments right here. So I've tried to be kind of consistent that AD is over here. That's all the same. So continuing with this proof, what I can do here is I can think of two right triangles. So I've got the Pythagorean theorem for this BCD. This is what I did before, and for this BCD over here. And once I figure out the Pythagorean theorem in terms of A's and H's and C's and X's, I come out with this. And for this obtuse triangle, I come out with this. Taking that a step further, now if I look at the other right triangle in both cases, so I have this right triangle here for ACD, and I have this right triangle here for ACD. I can rewrite this as x squared plus h squared equals b squared, or x squared plus h squared equals b squared. So that's the same for both of them. And then just like I did in the last example, I wanted to substitute out something for h squared. So if I rearrange this, h squared should equal b squared minus x squared. And what you can see in this next step is I've taken that b squared minus x squared and I have substituted it in for wherever I see an h squared in this equation and wherever I see an x squared in this equation. That's where these two come from. So once I substituted that, let's see where this goes next. I can look at let's look at the acute triangle. That's the one on the left. That's this one. And I can write up a cosine of A. Angle A is going to equal this adjacent over this hypotenuse side in this right triangle. Solving for x, I get b cosine A equals x. And once I substitute that into this x right here, I get a squared plus a squared equals b squared plus c squared minus 2bc cosine A. So that's making those substitutions for that h squared, making the substitution for this x into this Pythagorean theorem equation. For the obtuse triangle, I'm going to do the same thing. This one involves a little bit more creativity here because this angle, what is this angle? CAD, this one right here, is an angle of 100 minus a degrees. And the steps really look very similar where I have the cosine of 180 minus a, that's that angle, equals this. Here's the kicker to kind of wrap your mind around here. The cosine of 180 minus a equals the negative cosine of a. And let's kind of gather what that means. If you think about your unit circle, I've got some angle over here in my second quadrant. This would be my obtuse angle, and this angle over here could be A. That's my reference angle. So that means that this entire angle should be equal to 180 minus A. And if you think about the cosine of this angle, the cosine is negative in that second quadrant, and that should look a lot like if I just looked at angle A in the first quadrant. The cosine is positive here. These x values, the size of these x values, should be the same, except this one's positive and this one's negative. So really, if you just take the negative of the cosine of A, that's really the same thing as the regular old cosine in that second quadrant. So hopefully that makes some sense, because once I substitute that in, I come up with the same formula that I did over in this triangle. So like I said, this is a long process. You don't need to memorize this or really even be able to repeat it, but I want you to make some sense that these steps follow a logical order, because the law of cosines is this equation. This is the thing that you need to memorize, the thing that you need to understand, the thing that you have to be able to use. And you'll notice it kind of looks like the Pythagorean theorem. If I were to, let me write this again, just so I can jot some things down. If I were to look at the law of cosines, like I said, it's kind of like the Pythagorean theorem. Except now we have this trig stuff. We've got this 2bc cosine A, and no longer is it a squared plus b squared equals c squared. No longer are you thinking about a leg and a hypotenuse. That is right triangle stuff. In this case, just think of it as a side and a side and a side. The only thing that you might want to add to this is to think of this as so you've got some included, or whoops, over here this A should be like your included side, or rather included angle. Because really this is kind of like a side, and this is like another side, and this is like another side. These are all just three sides of a triangle. And really the only thing that differentiates the other sides from the other sides is that this A in this cosine equation is whatever the angle is between the sides B and C. So I mean, let me show you what I mean by that. If I have a triangle ABC, if I have side B and side C, A is the angle in between them. So that's kind of the scenario that you use here. Really, it doesn't matter your A, your B, your C, but think of it more as like a side, a side, a side, a whole bunch of sides, and then angle that is included between these two sides here. So now that we have the law of cosines as this equation, we're ready to apply it. So let's see an example of how to use this whole thing. Right now I have a side, an angle, and a side. That's one of the scenarios that I'd like to use for the law of cosines. So let me just jot that down again, so we can use it as a frame of reference. So I have a squared equals b squared plus c squared minus 2bc cosine of a. And again, you don't need to think of it as like hypotenuse and legs, but really it's just the angle A is included between sides B and C. So this is kind of like what side A is. And actually in this triangle, it is side A. So let's plug stuff into the formula. I want to find the length of BC here. So moving along in this equation, I have BC is going to equal, or BC squared will equal, doesn't matter which you choose as B or which you choose as C, you're just adding them up. So I've got 15 squared plus 21 squared minus 2 times 15 times 21 times the cosine of A. And actually, I don't need to write A because I know the angle. It's 105. So that's times the cosine of 105. Moving along, I can multiply some stuff together or square these, add them up. This comes out to be, I'll take it one step further, 441, I guess that's the 21 squared, plus 225, minus, multiplying these three together, I get 630 times the cosine of 105. I type this into my calculator and I get BC squared equals some 829.055, and it keeps going. At this point, you need to take the square root of both sides. So in my calculator, I'm just going to hit the square root of the answer. That's this. So I can kind of retain as many digits as I can. And the final answer this comes out to is BC equals 28.8 centimeters. So that is this side right here. So law of cosines. I have a side, an angle, and a side. I'm plugging stuff into a formula, and I'm figuring out what that opposite side is of this angle. So why don't you try this next example. It looks a lot like the other one. We've got a side and an angle and a side. Try and use that law of cosines equation. Pause the video and resume when you're ready to see the answer. All right, so here is my work for this law of cosines problem. Take a look at it, pause it if you need to, and we're going to move on to the next example. The law of cosines can also help us find an angle. So what about the case where we know a side, we know a side, and we know a side, and we want to find an angle? So this would be like, I have this, I have this, I have this, but I want to know what one of these angles could be. We can rearrange this equation to solve for the angle A rather than the side A. So in order to do that, we're just got to do some algebra. I'm going to subtract b squared, subtract c squared from both sides. So I get a squared minus b squared minus c squared equals negative 2bc times the cosine of a. I want to get the cosine of a by itself, so next up let's just divide everything out by negative 2bc. Divide all of this by negative 2bc. So I have a squared minus b squared minus c squared all over negative 2bc should equal the cosine of a. And really we can kind of leave it there. I don't really like leaving these negatives down below, so what I'm going to do is I'm going to just almost like multiply top and bottom by a -1 and move that negative to the top. So I like to write this as b squared plus c squared minus a squared over 2bc. And so this would be kind of rearranging your equation to help you solve for angle A. Now really at this point we could take it a step further and I could solve for A by taking the inverse cosine of this whole thing, but I'll just leave it like this for now. And again, it doesn't matter what your A is, what your B is, what your C is. Really I want you to think of this angle A is the included angle between B and C. That's kind of how I remember this, how to use this equation. So let's see an example. I've got, and there's if my handwriting wasn't very good, which it normally isn't, you can rewrite this equation in this form here. Let's see an example of what this looks like. So I've got this side scenario where I've got three sides of this triangle, and I want to find the measure of BCA. That's this angle right here. So let's use the law of cosines, and we're going to solve for the cosine of A. So the cosine of A is going to equal b squared plus c squared minus a squared all over 2bc. And really, again, like I said, it doesn't matter what b and c is. What matters is that A is the included angle. So I want you to think of this as your angle A. And then, of course, side A is whatever's opposite of that side. So let's plug stuff in then. So I'm going to put in the cosine of A is going to equal 5 squared plus 8 squared minus, this would be A, 7 squared, all over 2 times 5 times 8. So the cosine of A is going to equal 40 over 80. Once you calculate what the numerator and the denominator is. Another way of saying that is the cosine of A equals 1/2. Now I don't really need to go to the calculator because we all know this special angle, this should be, A is going to be 60 degrees because a 60-degree angle gives me a cosine of 1/2. And there you go. I have figured out what the cosine of, or rather what angle A is, but it's not really angle A, it's angle BCA. So really I guess this is my final answer here. So that's how you use that cosine, law of cosines solved for the cosine of A given three sides to find an angle, and that's missing. So why don't you try in this example, very similar problem. You've got three of these sides. You want to find this angle here. So again, think of this as if it's your angle A. Pause the video, give it a shot, and resume when you're ready to see the answer. All right, so it looks like I've kind of squeezed this a little bit here. Let me reshift this. And here's my work for this example here for you to try. Hopefully it went all right for you. Take a look at it, pause it if you need to, but this came out to be 111.8 degrees for this angle. In summary, in general, you want to use the law of cosines in specific circumstances. So law of sines is good in certain circumstances. Law of cosines is good in certain circumstances. And you'd want to use the law of cosines when you have one of two cases. If you know a side and you know an angle and you know a side and you want to find another side, or if you want to find other angles for that matter. And then the other situation would be is if you know all of the sides but you want to find an angle. Law of cosines is the only way you're going to be able to figure this out. Law of sines won't work for these scenarios. It's just not enough information to use the law of sines. So this is where you would want to use the law of cosines. Hopefully that makes some sense. feel free to go back and check over this stuff. If you need a refresher on the law of sines, watch that video again. But thanks for watching, and hopefully this was helpful.